Thanks, Sean. Morning, everyone. So as Sean said, my talk is going to be about wave breaking today. Relatively vague title. I'll explain exactly what it's going to be about in a second. But first of all, I thought I'd kind of introduce myself. I'm nowhere near as experienced as our speakers yesterday, Jean and Fabrice, but I thought I'd kind of demonstrate my credentials to show that I maybe do know a little bit about wave breaking. So this is me in the lab, looking at breaking waves. And yeah, hopefully, perhaps having spent the past few years looking at wave breaking in the lab, I can offer some interesting perspectives on the problem. So my talk is going to look at kind of three main questions today. And Fabrice kind of gave us a brief to make these talks kind of a little bit educational, a little pedagogical. I've started with the best intentions, and I may end up presenting a bit of my own work. But yeah, the three questions are essentially, what is wave breaking? When do waves break? So this is about kind of, can we predict wave breaking, essentially? And then the third question is essentially, what are the effects of wave breaking? And I've graded this one out a little bit because essentially after my talk, Lionel will be talking about dissipation, so I think this serves as a really long introduction to his talk, potentially. But yeah, I'm going to start off by looking at these questions predominantly in 2D, and then I'm going to move to 3D and essentially look at the implications of that. Now, I thought I would also start off with a little bit of a disclaimer. So I think yesterday Fabrice said that we should be in the real Earth environment. I'm going to take us out of that Earth environment and ignore a lot of effects that could be quite important. So I won't be including the effects of wind, current, rain, sand, and I'm mainly going to be talking about breaking at dominant scales. So this means I'm not thinking about things like viscosity necessarily, surface tension. It's mainly kind of the potential flow type of wave breaking that I'll be looking at. So this may seem like a really easy question to answer, but I don't necessarily think it is. And particularly when we start to move into 3D, it can become an even more difficult question to answer. So what is wave breaking? So I know it's relatively early in the morning, but I thought this video should look kind of weird to most of you, right? And the point I'm trying to make is that wave breaking is an irreversible process. So essentially, waves become overly steep, triggering this irreversible process of mixing, air entrainment, and energy loss. So that's what I would categorize as wave breaking in a very kind of broad sense, and I'll be a bit more specific in a second of what the actual implications of that might be or what it means. So people have been trying to kind of work out why breaking happens or what triggers breaking for a while. I think a fairly good explanation comes from Longet-Higgins. I don't think I've probably ever given a presentation where he's not done something on what I'm doing before me. And essentially, he tried to kind of explain the kind of initiation of wave breaking, at least in 2D for monochromatic waves, using this principle of superharmonic instability. So essentially, when you have a really steep wave on a high surface slope, you get these kind of surface perturbations, and over time they grow exponentially, which causes this kind of overturning motion. I don't normally criticize Longet-Higgins, but I think it's really weird having the waves propagate from right to left. But you can kind of get the point from these images, what's going on. More recently, we've had some work by kind of Mike Banner and his group looking at the energetics of this. So what they've done is essentially taken different parts of the kind of energy composition of a wave, kinetic energy and potential energy, and looked at how these different components are kind of transferring between each other. And these three kind of rows here show three different waves. The bottom two are breaking, and what they found is kind of immediately prior to breaking, you see this buildup of kinetic energy. And then when they plot the different components of energy against each other in this panel here, basically the breaking waves have this kind of point of inflection. So they thought potentially this kind of, there's an energetic signal of this breaking inception that might occur before kind of the kind of visual or kind of kinematic identifiers of breaking onset. So we do have some kind of theories that can kind of give us an understanding of what constitutes wave breaking in 2D. So the next question is essentially, when do waves break? And what I'm coming at from here is essentially, can we predict it? And there's a lot of research gone into this because it's a really important question to be able to predict breaking reliably for things like design and wave modeling in the ocean. So generally speaking, we would look at kind of predicting wave breaking using two classifications of criteria. You can kind of subdivide these a bit more, but generally speaking, we have geometric criteria on kinematic/dynamic criteria, and there's sometimes those two words kind of are used a little bit interchangeably. But yeah, first of all, geometric criteria, we would take our measured wave, look at the wave height or the wave amplitude, and then non-dimensionalize that by some length scale. So here we've got wavelength, which we would normally convert into wave number, and calculate something like AK or KH over 2. Alternatively, if we're looking at a kind of kinematic or dynamic parameter for determining when we might get breaking onset, we might look at something like the crest velocity of our wave and the fluid velocity of our wave. So we're looking at actually kind of internal kinematics of the waves or properties of the fluid. Now, there's been a lot of attention on this kinematic parameter, or sorry, dynamic parameter they call it, for wave breaking onset from Mike Banner and his group, which they call BX. And essentially, it's just the ratio of fluid velocity to crest velocity. And the idea is that when this value is greater than 0.855, you're going to get wave breaking. And they call this a wave breaking onset parameter. So this is occurring after the inception, which is indicated by this energetic signal. And this is just a few of the papers they've published. Other people have been using this as well. But I was just kind of showing that it has been relatively well validated for a range of different water depths, different types of breaking waves, kind of shoaling waves. And there's also been a paper looking at using it when they have vorticity present. That said, I would suggest that this isn't perfect. So measuring crest velocity isn't really a well-defined property. You have to somehow track the crest of a wave. If anyone's tried to do this, they might know it's not that easy, and it can be a little bit unstable. And then when we move to 3D, what is a wave crest? It becomes really hard to define what a wave crest is in 3D. So it's not always actually that easy to use something like this. So going back to that last slide, there's a really good review actually on a lot of this by Mark McAllister from 2013 that goes through all these different types of criteria. But in general, I would say most people, if you ask them, is a geometric criteria good at predicting wave breaking, they would say no. So I've put this big cross here, but then I'm going to revisit this because if you speak to people in industry, or you speak to a lot of people who are doing kind of calculations in design and stuff like that, most of them are going to use geometric breaking criteria, just because they're really simple and they're kind of easy to understand. And I think also there's potentially a light at the end of the tunnel for geometric criteria too. So I'm going to present a little bit more on that. So what's wrong with them? Well, this figure kind of to some extent demonstrates what I think is the perceived issue with geometric wave breaking criteria. So on the x-axis, I'm just plotting steepness. And then there's two panels here because these are just two different measures of bandwidth. It's not really important why I've done that. But I'm plotting the steepness at breaking onset for all these different studies here that I could find. And these are all just two-dimensional studies of wave breaking onset for focused wave groups where I could find a kind of comparable measure of steepness, loosely speaking, to compare. And if steepness, in this sense, was a good parameter for predicting wave breaking, you would expect these lines to collapse onto some kind of curve. And I'm going to say they don't. And I'll explain potentially why I think they don't. And to do this, I basically carried out some simulations using the Doldom-Peregrine code with some help from Nick to essentially look at wave breaking onset, but kind of take a really detailed look at essentially if we can use various different types of steepness to predict wave breaking onset and understand exactly what's going on with all these kind of fairly divergent experimental and numerical results that exist in the literature. So first of all, it's worth being really specific about what we mean by steepness, because people define steepnesses in different ways. So you can define steepness globally, so it's not necessarily like a geometric parameter, but it's still kind of a steepness parameter, where you would essentially take your frequency spectrum for your waves, and then you would just sum up all the discrete amplitudes and wave numbers, and that gives you like a global steepness. And this is what people do sometimes to define the steepness of their waves. And yeah, as I said, that's the kind of representation of how steep your spectrum is, not necessarily the wave. And then alternatively, you might look at something like a local steepness, where essentially you do take your measured surface elevation, take the wave height or the wave amplitude, non-dimensionalized by some length scale. And then this figure here is just plotting what happens if you take these two different measures of steepness for these numerically simulated waves at breaking onset. So the gray dots here are non-breaking waves, and the red dots are breaking waves. The main thing to take away here is that essentially you get a different functionality for the two different measures. So one goes up with bandwidth, the other goes down. So if you start to be a bit more careful about essentially the measures of steepness that you take from the literature, so you take only global steepness on one side, local steepness on the other side, the data looks a little bit less rubbish. And these two parameterizations here are existing parameterizations from experiments by Wu and Yu and some numerical simulations by Nick, where they've plotted essentially global steepness versus this bandwidth parameter delta and local steepness versus the kind of more commonly used bandwidth parameter nu. And what you can see is that the data starts to look a little bit more like it could collapse onto a curve, but there is still some offsets and some differences between these studies. And so this final addition to the figure shows essentially the different spectral shapes that correspond to these different studies. So what we're kind of seeing here is that different spectral shapes are enough of a difference between these experiments to cause steepness to be a poor indicator of breaking onset by these two definitions. But in doing these experiments, I essentially carried out, well, it's not experiments, simulations, lots of different simulations of lots of different bandwidth wave groups with lots of different with lots of different underlying spectra. So I'm kind of varying everything apart from water depth that you could vary in 2D. And I started looking at another measure of geometry that's slightly different to these two, which is just local slope. So I was looking at the maximum local slope of these two-dimensional waves prior to breaking. And I've taken all these different simulations and just kind of made them an individual marker on these figures. And everything that is gray here is a non-breaking simulation, and everything that's red is a breaking simulation. And so if we actually look at the local slope, or the maximum local slope that these waves achieved, we can see that all of the non-breaking waves lie below this dashed line in panel A, and all of the breaking waves lie above that dashed line. And the dashed line sits at a slope of 0.5774, and that's essentially an angle of 60 degrees, which is the same slope you'd get at the front of a Stokes wave. So there's potentially some interesting coincidence there, potentially not. And I'm just comparing it here to the kinematic/dynamic breaking parameter presented by Bartholomew et al. And we can see that kind of both parameters are doing a relatively good job of essentially predicting breaking, non-breaking waves. But this slope-based one in panel C, you can see, has a bit more separation between the breaking and non-breaking populations. And yeah, both these horizontal lines just show the threshold values of these parameters. So the cool thing about a slope-based parameter is it's actually a lot easier to measure than fluid velocity and crest speed. So there's a potential usefulness in this for kind of experiments, because it's much easier to measure slope, as I said. So next up, not all waves look like this. This is an amazing video that I didn't give them credit earlier. Martin Ernan, Luke Dyke, and some of their collaborators created. And I don't think I ever need to try and take a video of a breaking wave, because I'm not going to do a better job than this. But yeah, not all waves look like this. I think Trygve might have used this image yesterday, and he cited it, I didn't, sorry. But you know, waves in the ocean are short-crested and a bit all over the place. So how is that going to affect our wave breaking in terms of definitions and onset? So just to kind of give you an idea of the kind of different options we can have for three-dimensional waves, this is just three animations showing kind of, at first, like a unidirectional wave, so this is what we've been looking at before, and then some kind of short-crested wave, and then at the far extreme, we can actually have axisymmetric waves. So I'm just trying to indicate here that when we start thinking about three-dimensional waves, there's a whole range of different things we can have. And I'm actually going to look at this kind of axisymmetric problem first, because it gives us some interesting insights to how different wave breaking can be in 3D. So yeah, when we have an axisymmetric wave, or something that looks a bit like this when it's breaking, how do we actually define breaking onset? It becomes a lot harder, and hopefully this is clear enough at the back. But this is a series of experiments I carried out where essentially I've made axisymmetric waves in a big circular wave tank. And going from the left-hand side of this figure to the right-hand side, we're increasing the amplitude of the waves. And what you can see is as we do that, we get this large jet of water forming. But when we're actually doing these experiments, it's really difficult to work out when the wave breaks or not. And with these experiments, you could tell it was breaking because essentially after the jet went up, it fell down and splashed against the water. But that was a long time after the breaking actually occurred. And for these smaller experiments, we had to kind of rely on actual sound when the jet was kind of collapsing in on itself. But the point I'm making here is when you have a standing wave, you don't have this obvious kind of overturning effect that you can really easily identify as breaking. So when you have these 3D waves, actually just detecting wave breaking can be really challenging. And you may think this is a bit of a weird extreme example, but if we make slightly more realistic sea states, where this is a kind of crossing sea state that we've created in the lab, we can get a type of breaking that does look a bit like a standing wave. So there are some kind of overlaps in the kind of breaking phenomena that we observe. And yeah, this was kind of inspired to an extent by a study that I carried out when I had a little bit of spare time in the tank, where we were trying to reproduce, so those of you who don't know, the Draupner wave was this freak wave that was measured in 1995 off a platform in the North Sea. And it was one of the first kind of confirmed measurements of a rogue wave or a freak wave in the ocean. And we decided to try and reproduce it in our wave tank. Well, not our wave tank, the wave tank we use. And what we found essentially was that if we tried to make it in a kind of following sea condition, we would get kind of fairly standard overturning, plunging type breaking. But if we decomposed the sea state into a crossing sea state, we could make the wave, we could reproduce the full scaled amplitude. But we got something that looked a bit more like a standing wave forming and this kind of jet type breaking. And that was the kind of inspiration for a grant that Ton and I wrote with Frederick Diaz at UCD about wave breaking and crossing seas. And this is the body of work that I'm going to show you now, which essentially looks at how wave breaking can change when we have three-dimensional waves. And I've mainly put this slide in just to make it clear that I didn't do all this work on my own. So Ton, obviously, is up there. We did this together with Frederick in UCD, Tom Adcock in Oxford, my colleague Sam Draycott in Manchester, Tom Davey and Ross Calvert in Edinburgh, and then James was a postdoc, James Steer in Oxford, and then we had Syed Hassan in UCD. And then we had a little bit of advisory from Jean Bidlot at ECMWF and Odin Gramstad at DNV. And then finally, we got to do some experiments in Shanghai, which I'll show you. So kind of returning to the problem of wave breaking onset, but for three-dimensional waves. I'm going to show you quite a few experiments from this circular wave tank in Edinburgh. And the cool thing about a circular wave tank is you can make waves that travel in any direction you want, so you can look at kind of all different types of three-dimensional wave breaking. So to kind of establish how three-dimensionality affects wave breaking onset, what we did was we essentially made lots of different wave groups, directionally spread. And so this is just a kind of diagram below these wave groups of what the directional distribution of energy would look like. So this is d of theta. And we essentially just define the kind of spreading of our wave groups using this value sigma theta, which is just the width of our distribution. And if we have a bimodal distribution, which we would call crossing, we use this parameter delta theta to kind of define the crossing angle between these two peaks. So we made lots of different wave groups with lots of different combinations of omega theta and delta theta, and then essentially just kind of increased their steepness until we observe breaking, kind of in an iterative process, to work out the point at which breaking onset is occurring for this range of conditions shown in the table here. And we just chose this range of conditions because we thought it represented kind of the majority of directional spreading that you might experience in the oceans. Cool. So this is just kind of giving you a little overview of what some of the measurements we managed to get looked like. So we installed a quite densely kind of populated array of wave gauges in the tank so that we could measure surface elevation with a nice spatial resolution. And yeah, these surfaces here are just showing kind of an example of the measurements we got at the time of maximum amplitude for a few of the different cases that I've kind of explained all of them to you a second ago. And in the top row of panels, this is just showing how the waves change shape as we increase the degree of spreading. And then in the bottom row, it's just showing how the waves change shape as we increase the crossing angle. The axes aren't necessarily super clear here, but as we do both of these things, the waves are getting considerably larger, and it should be clear from these that the waves are also changing their shape quite a lot. So how does that actually affect wave breaking onset? So this figure is essentially summarizing all the results of those experiments. So all the different markers correspond to all these different wave groups with different directional properties. And in this figure here, we're essentially plotting how the maximum local slope measured with our wave gauge array, or the global steepness that underlies those waves, varies as a function of a single parameter measure of spreading. So here we have this parameter omega naught, which is essentially just an integral measure of spreading width, which is the same thing that you would get out of ECWAM or WaveWatch. So it's essentially just an integral measure of spreading that goes from 0 for unidirectional to 1 for kind of as directionally spread as you can go. And what we can see, we'll start with global steepness because it's a bit less messy, is that the initial kind of global steepness at which we get breaking for our experiments is starting around about 0.3. I've just included this dashed line here because that's a kind of global steepness that I got from my numerical simulations that I showed you before for 2D waves. So it's starting at around about the same point, and then as we increase the degree of spreading, the global steepness at which breaking occurs is roughly doubling, and it kind of plateaus as well. And so I've just fitted a line here to show that we can kind of try and parameterize this behavior just using a single parameter measure of spreading. Around about here, there's a little bit of kind of, scatter in the points, but those kind of axisymmetric waves are not particularly common. And then moving to local slope, so the error bars here are quite large, and that's just because our wave gauges were spaced 0.1 meters apart, so when we're trying to estimate slope from them, there's a kind of relatively large error in our kind of finite differencing. Again, I've fitted a line to these to show that we can kind of try and parameterize this behavior. And I've also got this black dashed line, which is the same fitted line shifted up. And the reason I've done that is just so that this fit has the right value of slope at kind of omega naught equals 0. So this is the value of slope that we observed in 2D. And what I kind of think is interesting, which might not necessarily seem too interesting to the rest of you, is that this dashed line, I'm going to point at it because dashed and dot isn't necessarily clear. This line lies between these gray lines, and the gray lines are essentially the limiting angle of a Stokes wave at the bottom and the limiting angle of a standing wave at the top. So Penny and Price, I can't remember when it was, did the same kind of derivation for a limiting waveform for a standing wave and came up with an angle of 45 degrees, which is that top line, and then the kind of 60-degree angle of a Stokes wave is that bottom line. So once you account for the kind of error in our finite differencing, and you include these error bars, you could potentially suggest that the maximum slope of three-dimensional waves kind of lies within this kind of paradigm. So that's potentially quite interesting, I think. And then this is just a slightly different measure of spreading that I created, which essentially looks at how directionality affects the slope of waves. And if we use this one, we can actually get our global steepness to collapse onto a straight line. These contour maps on the left-hand side just show how our parameters omega, sigma theta, and delta theta kind of map onto these directional spreading single value parameters. So what's kind of causing this change? So, we're seeing that as we increase the directional spreading, waves are about twice as steep before they break. Well, in a kind of like phenomenological sense, we're seeing different types of wave breaking. So I showed you this GIF earlier. When the spreading is narrow, we see essentially kind of fairly standard overturning plunging wave breaking, which is not too dissimilar from what I've shown you in 2D. But when we start to have these kind of crossing wave groups, we see a kind of mixture of standing wave and kind of traveling wave breaking, which we've kind of tried to categorize into these three kind of regimes of breaking. So at one extreme, as I said, we've got kind of overturning traveling wave breaking that we're relatively familiar with. I can use this as well for people online. And then we have this, at the other end of the kind of regime, we have standing wave breaking, which again has been fairly well studied. But then in the middle, we have this kind of combination of the two, where we get kind of a ridge of water that kind of forms as these two waves cross, and we get this kind of standing wave breaking forming on top of it, which causes a big splash. One thing that I think is interesting that maybe touches a little bit upon the kind of third question that I asked is how do these kind of directionally spread waves behave after breaking onset? So in panel A, what I'm doing is showing some additional experiments that we carried out, where essentially we'd established the kind of steepness at which breaking onset occurs, but we then asked the wave tank to make waves that were 12% bigger, 25% bigger, and 50% bigger. So we're continuing to increase the amplitude of the wavemaker forcing. And then the kind of legend here just shows what directional conditions they corresponded to. And the x-axis is showing the kind of relative forcing. So 1 means it's just the breaking onset, and 1.5 means it's 50% above that. The y-axis is showing kind of a normalized value of what we measured in the tank. So all of these waves are directionally spread. Going from blue to purple, we're increasing the directional spread. And what we can actually see is for the most directionally spread, which is purple, we're able to produce a wave that was 80% bigger than at breaking onset. And 80% wasn't some hard limit, we just didn't do any more experiments because we had a finite amount of time. And I've just shown what the kind of surfaces of the waves look like for these purple markers in the panels to the right-hand side. So even though breaking has started, the wave can be much bigger if you try, you can continue to make bigger waves for the same directional spreading. And that has some interesting implications for kind of offshore design, because often from 2D kind of thinking, we would say that once wave breaking starts, our wave can't become any bigger. Whereas here we've got a wave that's 80% bigger than the wave at breaking onset. Cool. So now I'm going to kind of present something that potentially no one has seen before at WISE. Some of that was a bit of a repeat, which is about monochromatic crossing waves. So this is kind of taking a little bit of a step back in terms of complexity, which helps us kind of maybe understand a little bit more the kind of the physics of what's actually going on with these wave groups. So the monochromatic crossing wave problem is relatively well studied. And in a similar approach you might take to kind of studying a Stokes wave or a standing wave limiting waveform, it also kind of serves as a bit of a canonical problem because it has an analogy to waves reflecting off a wall or a breakwater. And so yeah, we just have two monochromatic waves, which I'm kind of just indicating with these lines here that kind of cross at an angle of delta theta. And this is the kind of wave pattern that we would get if we superimpose those two monochromatic waves. So there's a few different studies that exist in the literature. I've just included a couple of them here, where you would essentially take the boundary conditions, assume some kind of basis function, and search for coefficients of those basis functions so that you can kind of derive an equivalent to like a kind of limiting wave height that you would do for a Stokes wave or a standing wave for all of these different short-crested or monochromatic crossing waves. And when you kind of take these solutions and you find a maximum in the total energy, you can kind of say that's your almost limiting wave height, and you can come up with these points to show how essentially limiting wave height varies as a function of crossing angle. And what's kind of interesting from all these different studies is that there comes this kind of non-monotonic behavior of wave height, which is explained by Tsai et al. As this kind of playoff between kinematic stability and dynamic stability. So to the left-hand side of this red dashed line, essentially they're suggesting that we get breaking because of a kinematic instability, which can be parameterized in a very similar way to the Bartholomew parameter, which is just U upon C. Here they're using Cp because it's a monochromatic wave, so it's just a phase speed. So essentially, in this region, we're kind of getting an overturning type of plunging breaking. And then once we get to the critical value of crossing angle, we start to get breaking being triggered by a kind of dynamic instability. So this is essentially when the fluid in the crest achieves an acceleration of gravity. So this kind of gives some indication or some explanation of kind of the regimes of breaking that we're seeing in a slightly more kind of clean way. So yeah, we have these two kind of competing instabilities. Obviously, in our experiments, we didn't necessarily necessarily see such non-monotonic behavior, but we did kind of see an increase and then a plateau. So this panel here is just showing some experiments that we did to kind of look into this in the lab. So we're using our kind of wave gauge array again to measure the surface elevations for these monochromatic crossing waves. And we're just going from a kind of two-dimensional traveling wave all the way to a kind of nearly standing wave. And you can just see how the kind of wavelengths, that's what's shown in panel I actually, is how the kind of mean and transverse wavelengths are varying as a function of this crossing angle. And there's some quite cool wave shapes. Not too much to take from that otherwise. And these are how our experimental results compared to those theories. So these red dots here are essentially the kind of average steepness of different monochromatic kind of crossing angles as a function, different steepnesses as a function of crossing angle for these monochromatic waves. And we can see that we do have relatively large error bars, and I'll show why in a second, but we do reproduce this kind of non-monotonic behavior that we expect for the kind of almost limiting monochromatic waves. So the reason these error bars are relatively large, I'm actually pointing at myself. You can't see too well in this video. It looks a bit nicer on my laptop. But I had to spend a lot of time just staring at the waves because it was really hard to tell if they were breaking. And we were doing this visually, which isn't ideal, but it was kind of the best way we had in the situation. And once the waves have very large crossing angles, you get these kind of interfering crests that travel incredibly fast. So the kind of apparent crest velocity is super high. And it was quite tricky to work out whether or not they were breaking or not, but I think, within these error bars, it seems like we may have reproduced this kind of quite interesting non-monotonic limiting wave height behavior. And I would say that when you have monochromatic waves, using a local steepness definition like kh/2 makes a little bit more sense than when you have unsteady waves. But I was mainly just using that here because that's what the kind of literature does. Cool. So this is the last set of experiments I'm going to show. You can kind of take a breath. So we've shown that for kind of deterministic waves, directionality has a fairly significant effect on when wave breaking occurs. So as I said, we're doubling the steepness at which wave breaking is occurring. But I'm moving it back into reality a bit more now. So waves in the ocean are not wave groups. They're not monochromatic waves. They're irregular. So we did this final set of experiments to look at kind of random wave simulations in this huge tank in Shanghai. So the tank is 40 meters by 50 meters. And it has wave makers on two sides. So we couldn't quite make waves with the same kind of range of directional spreading as we can in the circular tank. I've just listed the kind of spreading conditions for the waves here. And what we did was we created a range of different sea states with different significant wave heights so that we could try and investigate the kind of proportion of waves that were breaking in these experiments. So you can see in the kind of diagram, there's a little camera in the top corner. And I'll show you some images from the camera in a second. But essentially what we did is we varied the kind of sea state parameters and then used the camera to measure the proportion of breaking waves. So we could see how our kind of deterministic effects on how breaking onset steepness changes kind of relate to random wave trains to see if there are fewer waves breaking. Right, so these are just some images that haven't come up too well on the projector. We're essentially going from top to bottom, we're increasing the significant wave height, and then going from left to right, we're just increasing this crossing angle in our directional distribution. And you can kind of try and take a look at this and see whether or not you think if there are more white caps as we increase the crossing angle or fewer. But definitely you can see as we go from top to bottom, there's more white capping happening. So that's kind of somewhat reassuring. But to kind of quantify these results in a more kind of quantifiable way, we have essentially just calculated breaking probability. So what we did is we took those images with a little bit of help from Lionel and his student Bernard and did some white capping analysis. And we would pick, the cameras weren't calibrated because they weren't essentially designed to be used for this analysis, but we kind of decided to do it after the fact. So instead of using a kind of conventional white capping kind of lambda seed distribution, what we did is just chose 50 random locations in the experiment, and then every time a white cap passed that location, we would count that as one breaking wave out of the population of all the waves. And this is kind of a similar approach as used in some earlier work by Banner and Babinin and Young. And so essentially what we're presenting here is BT, which is a breaking probability. So this is the number of breaking waves divided by the number of non-breaking waves. And then going from left to right, we're just increasing the significant wave height of our experiments, and we're plotting the breaking probability as a function of crossing angle, and then these two different marker types just indicate the directional spread of those C states. So going from left to right, the proportion of breaking waves goes up with significant wave height, which makes me think maybe the analysis wasn't necessarily wrong. And kind of increasing crossing angle, or increasing the overall degree of spread, reduces the breaking probability. So that's kind of in line with what we've been seeing in these deterministic cases. So to kind of plot this in a slightly different way, we can kind of compare our results to a few existing breaking probability models. So there's one by Mike Banner and Alex and Ian from 2000, which is shown by this dashed line. And essentially they're saying that they fit an empirical relationship between epsilon, which is this kind of peak wave steepness. So it's a kind of spectral wave steepness calculated plus or minus 0.3 fp times the peak. And so this was based on in situ data. So this does kind of implicitly include some effects of spreading, but not directly. And then we have two other breaking probability distributions, one by Filippo, which essentially takes a Rayleigh distribution and multiplies it by a weighting function, then you integrate the product of those to get a kind of probability of breaking. And then finally, there's this Stingari approach, which was published recently, where they're using Gaussian field theory to essentially work out the probability of given values of U upon C. And I've got two lines here for that distribution, because depending on which U upon C you use, you get a different breaking probability. But what's interesting here is, if you see the data that I've plotted, I've color-coded each different significant 5 minutes cool, each different significant wave height using a different color. And what you can see is that the kind of increase in breaking probability coming from significant wave height is almost as big as the increase in breaking probability coming from directionality. And so a lot of these, like, you know, as I said, the Banner paper does implicitly count for spreading, but the others say that spreading is potentially a secondary effect. But what we can see is the variation is just as large. And one of the observations we had from these experiments was that essentially we could kind of account for this effects of spreading with this linear correction based on the omega naught, our spreading parameter, to try and get our results to collapse onto a curve a little bit. But then James, the postdoc working on the project, came up with a slightly more elegant way of kind of accounting for the effects of directional spreading to produce a wave breaking model. So essentially what we've done here is we've used this PDF for surface slope that comes from a paper by Longa Higgins in 1957. So it's just a linear approximation of how surface slope varies, which is a function of the underlying directional spectrum. And then we use this maximum value of slope from my experiments, and we essentially say, for a given directional spreading condition, any waves that are on the right-hand side of this line are breaking, and that gives you a breaking probability model that accounts for directional spreading using our empirical results. And if we compare that to the data, this is essentially, I did notice that I've used PT in my figures, James has used PB, but they're the same thing. And if we plot our results versus James's model, we can kind of get them to collapse onto a relatively good curve. It's not a one-to-one fit, so there's obviously like a kind of factor of 2 or something like that going on here. The gradient is 0.45. But basically, if we correct this model, it's doing a really good job of predicting breaking and accounting for the effects of directionality. This figure here just shows what happens if we were to use James's model, but assume a fixed directionality and compare it to our results, so the kind of quality of prediction goes down quite dramatically. So we have a model that we can kind of say is based on our results, which seems to reproduce the experiments relatively well to predict breaking probability that accounts for directionality. So, how much time have we got left, John? I think this says I've got 39 minutes on this. Cool. So, I'll go very quickly. So what are the effects of breaking? Well, this is for Lionel to really continue speaking about. I just wanted to put these videos in because they're really cool. So these are some infrared images that I took of some of the breaking waves I've shown you today, where we've heated the surface of the water. It's yellow on top where it's hot, it's black on the bottom where it's cold, and this just shows how the kind of mixing that we get for a 2D wave can be quite different for a 3D wave. We're not really learning anything about the depth dependence of this, but there is potentially quite significantly different mixing processes for these different types of breaking. Returning to this spike wave, we can actually see in this video here, when we get this little jet forming, there's a kind of circle or a ring of bubbles that is created by this, which is quite different to the entrainment you would get for a traveling wave. And if we make this even bigger, we can see this plume of bubbles, so this would be interesting to Trygve, that goes all the way to the bottom of the wave tank. So this is very different to wave breaking that you might see in 2D, which is the way that we build some of our inertial dissipation modules. So I think I've probably answered how these questions might vary in 3D. So we have essentially quite significant differences to wave breaking onset. Waves break at much higher steepness, and potentially the dissipative and mixing mechanisms are quite different. So perhaps I should have started my presentation with an image like this. And before anyone says waves like this don't happen in the ocean, they do. So hopefully you find this interesting. These are some of the papers that we're kind of working on / are published already if you're interested. And yeah, this is just again to emphasize that I didn't do this on my own. There's lots of names. There's a few names that pop up quite regularly. So thanks very much.